Let's get into symmetric ciphers. All right. Symmetric ciphers. Single key for both encryption and decryption. Also known as shared key, single key, secret key, private key. One of the biggest problems here is managing those keys. If you know that you have to use encryption because the medium you're passing the message over is untrusted, how do you get the key to someone else to begin with? What's the answer for that? How do you do it?
Diffie-Hellman.
Say again?
Diffie-Hellman.
Diffie-Hellman is a good way of exchanging keys. It was actually created as a key exchange methodology, and we'll get to that in a little bit. What's another good way to do it? What's probably the best way to exchange keys?
Tell them.
Out of band, right? Don't send it over that medium. Do it a different way, right? Call them on the phone, see them in person, send them a letter. What is the highest classification of DoD material that can be sent through the U.S. mail?
Secret can.
Secret. Yeah, secret. Do you mark it? You say secret on it?
No.
No, you don't. No, you don't.
You put top secret
Yes. No.
on the material of the
Trust me,
inner.
this is an
What's that?
Don't look at
On
it.
the inner material.
On the inner material, not on the envelope. Yes, exactly. Yes. The labeling should stay on the inside. Good. Why is it safe to do that?
What?
Why is it safe to send secret material through the U.S. mail? Anyone can touch that stuff, right?
But it's a federal offense if you open up someone else, right?
Whoa, well, that'll stop you.
No, but I'm
Stop me already.
If-
Should be able to use our federal mail to send federal stuff.
Okay. It has to do with volume, too. I mean, to actually try to establish, where that secret is. You're hiding, yeah, it's needle in a haystack kind of stuff. Exactly. Good. Good. Hiding in plain sight also. Advantages, some of them are even free. Disadvantages, you're not getting the non-repudiation. You're not getting the integrity or the access control. You're only getting the confidentiality. You're only using that form of encryption to keep stuff secret. These were symmetric ciphers. They had the same key. In the Scutali, what was the key? The rod, diameter, and taper itself, right? They had to match. Good. In the Enigma, what was it?
Position of the discs? Or
Yeah.
the discs themselves?
The disks themselves, and then the daily key was also sent out also. And in the Caesar cipher, it was knowing what the offset was going to be. Good. You're using one key, the same key. Your plain text goes into your algorithm. Along with the key, it results in the ciphertext. It's sent over that medium, that's untrusted medium. The recipient uses the same key, runs the same algorithm, and gets the plain text. Simple, straightforward, makes sense? Good. Questions on that? Data encryption standards. DES. Harst or Horst Feistel, depending how you look at it, had this concept of taking the plain text, chopping it in half, and using it to do the exclusive OR operation against itself, and then repeating that operation as needed to add more complexity. That was a very popular mode of encrypting things, all the way up through, wow, I'm so used to saying this century, but that's not the case, no. Up through the late 20th century, right? It used the Lucifer algorithm, but it had smaller key length. And it was supposed to be 64 bits. Anyone know why? What the purpose of that was going to be? Why'd they make it so small? It fit on a single chip at the time. Okay. But that actually came down to 56 bits, the 8 bits for parity. What's parity? What's parity?
RAID 5.
Huh?
RAID 5, yes.
RAID 5.
Error checking.
With error checking. Good. Good. So you can check each message to make sure that it's what it was when it was sent. Good. Basic block ciphering modes that we talked about. Same kind of thing. But they also had other modes that you could make it appear as if it was a stream cipher. For instance, cipher feedback mode. You're going to break it into segments. When you started the process, you put the initialization vector into the shift register and then sent it through the DES process, the algorithm. You're going to keep feeding it back into the register and transmit it to the receiver. And you keep doing this until the end. And we got a graphic for that, too. And output feedback mode, similar to that, except you're going to use the key stream to feed the shift register. Counter mode is similar, but you actually have a key that you've pre-generated. Not a key, I'm sorry, a counter that you've pre-generated. That becomes your initialization vector, and then it's incremented for each block subsequent to that. Okay. Okay. So this is the ECB method that we talked about already. Is ECB that good? No. Why not? Why not?
Repetition.
You're just repeating the same things over again. The same plain text is going to give the same ciphertext from block to block, allowing frequency analysis. All right. So that's ECB.
Trojan horse.
Cipher block chaining, we already talked about. You're going to use the output from one to be the input for the next. Cipher feedback mode. It's the one we were just talking about. All right. You've got your key, your IV, both going into the algorithm. You're going to take that block. You're going to get rid, of course, of the rest. You're treating it in the blocks. The plain text is also a block, and that ends up with your block of ciphertext. That ciphertext goes on the end of the next shift that you've got. That becomes your next initialization vector. Again, you're going to rekey it, send it through, take the sequence, that block, get rid of the rest, and do it again on the next sequence of plain text. So if this was bits 1 through 8, this would be bits 7 through 16, and you'd keep doing that until you get to the end. Does that make sense? Strong? Good? Yeah. Yeah, that one's pretty good. That one's pretty good because you're not going to have the repetition that you had in the other ones. In the feedback mode, in the output feedback mode, what's different here? What are we doing differently here? Yeah. We're doing our exclusive OR operation right before, instead of feeding it back into the algorithm, right? Is that stronger than the previous mode? Stronger or weaker? We would have exclusive OR here in feedback. Stronger or weaker? Is it adding complexity? Yeah, it's adding a bit of complexity. It is a better method for doing it. What's the problem with it, though? Takes more resources, right? You're adding another operation. It's going to slow it down a bit. Good. This is the counter. This is the counter method. Because we already have pre-calculated our counters and we know that we can shift them right along, we're treating them, we're treating the blocks separately. What can we do? What ability do we have in counter mode that we didn't in the others? We can run them simultaneously. We can do them at the same time instead of doing them in sequence. This operation is not fed with output from this operation, so we can run them all concurrently. That's why counter is used in high-speed applications. Does that make sense? Stronger or weaker? What's that?
Weaker.
Why?
Still no chaining.
Yeah. You're not because you're not using this ciphertext to feed this next process, while you won't have repetition because you're incrementing your counters, you still are not getting as complex as the previous operations were. You have something that's already known. Good. Questions on those? Questions on those? They're nuanced. All right. Why is DES good? It's robust. It stood the test of time. It's been in the family for quite a while. Why don't we use it as much anymore? Why shouldn't you use it?
It's got weak S boxes.
What's an S box?
You know, right?
Black box. You don't know.
I'm going to go with that. I like that answer.
What's that?
You don't know.
You don't know what?
You don't know what's inside the S box.
You don't know what's inside the S box? What is the S box? What is the black box?
It's the number of characters you're selecting.
Okay.
Since it's only 64, it's pretty small.
This is what you're grabbing, right? This is what you're deciding your chunks are going to be, right? Why is 64 not suitable?
It's a pretty small domain. Doesn't give you many bits of entropy.
It makes you susceptible to what kind of attack?
Just
Brute force, yeah. Because you can try all the possible responses, right? You could generate the ciphertext, all the possible ciphertexts that a message of that length might have, and you can check them against the possible plaintext, the ones that aren't gibberish.
which is what people have done.
Yes.
Just download the tables.
Yeah. So, because we can do this fast enough, and because we can get the results, it could be cracked. So what do you use instead? Well, there's double DES. Do the DESing, and then do it again. Does this make it more complex?
Yes.
Yeah, sure does. What's a meet in the middle attack? Not man in the middle, a little different. We're not talking about interception. It's what we were just talking about. By taking all the possible keys and trying to see what doesn't result in gibberish, you can find the ones that match and then determine what the key was between that plain text and that ciphertext. Again, is the DES operation secret? Is it something that nobody knows? No. That would violate the Kirchhoff law, wouldn't it? Yeah. Everyone has access to it, so it can be used by attackers to try to brute force things. So what's triple DES? I know. This one's complicated. This one's tricky. Mike, help us out.
It's actually different than double DES.
It is different than double DES. But are we DESing it 3 times?
No, you encrypt, decrypt, encrypt.
You can. You can. Does that add real complexity?
Yes,
Big time.
No.
it does.
No, it doesn't.
If you rearrange the order, it's weaker.
If you rearrange the...
Like if you decrypt, encrypt, decrypt, it's weaker. Or sorry, encrypt, encrypt, decrypt, it's weaker.
If you encrypt, encrypt, decrypt, it's weaker?
Yes.
Then what? Then encrypt, encrypt, encrypt?
Then encrypt, decrypt, encrypt.
Also, double des isn't too far from just regular des.
No. And here is one example of how you can do it. And yes, you can encrypt, decrypt, encrypt. Is it necessarily stronger? No. You have all the variants there that you could run, but mathematically, all you're doing is running the operation in reverse again. It's not.
Well, how would you change it? That wouldn't make it weaker.
No, but it's. I'm sorry, it's not weaker. It's as strong as encrypting it again.
Okay.
All you're using is another ciphertext input. Why would decrypting it make it stronger than encrypting it again?
Well, because of
you
the way
use a
that
different
DES
key.
works, and because of the S boxes, actually, a double decrypt is as secure as a single encrypt. Or, I'm sorry, a double encrypt is as secure mathematically as a singular encrypt. But by changing it and using a separate key to do a different decryption in between, you're actually increasing the complexity, as opposed to basically making it the same.
Second key.
Yeah,
Increased your bits.
well, it's not just a second key, because even with a double decrypt on a different key, it's still relatively the same. It's just a single encrypt. You don't want to repeat the DES process, any one step of it twice, basically. It's part of the reason why we essentially skipped straight from single DES to triple DES.
Okay, all right. I like that. That's very good. That's a very good explanation. Good. All right. AES. The feds decided to go with AES instead of DES in '97. Other finalists in that competition included Twofish, IDEA, and RC5 and 6. Who's Twofish? Oh, I think we're actually going to get to that in a moment. Triple DES. We still use triple DES? Yeah. Triple DES is still useful. AES is based on Rindahl. Where do we get the name Rindahl?
The person who created it?
Yeah. It's actually the two surnames of the creators put together, which I'm not going to remember offhand. But yes, it is their names. There's a variable block length in Rindahl, which can be, I think it's up to 256. Is that correct? Okay. AES uses the 128-bit version. You also have various key lengths that you can use. There are 4 operations in AES. Start with the substitution, then transposition. Then you mix the columns based on the actual data values in the columns and do a round key at the end. In Rindahl, we're going to take, if we're using AES 128-bit, we're going to take that 128-bit block and we're going to put it into an array. Why are we doing this? Why are we arranging it in this fashion? Matt? Why are we splitting the block up into a matrix?
Well, because math likes matrices.
Okay, all right. Make it easier to calculate, make it easier to arrange.
Prettier
All right.
graphs.
What's that?
Prettier graphics.
Prettier graphics. All right. What is it that we're going to transform? How are we going to move? How how are we going to move these bytes around?
Based upon the algorithm.
Okay, CCMP. Counter mode with cipher block chaining, authentication code protocol, part of 802.11i. It's based on AES, and it's got confidentiality. Do we still use WPA2?
Yes.
Yeah. It's not a bad standard to use. I could have swore we had a graph for that too. Yeah. Okay. Other symmetrics, IDEA. Another replacement, one of the finalists in the 1997 competition to replace DES. It's got the 128-bit key, similar to AES, but 64-bit blocks. 8 rounds of transposition and substitution using the mod and the exclusive OR value. Cast. Where'd they get the name cast?
Carlisle Adams.
Whoa, you're good at decryption. That's pretty awesome. That's good. Yeah, code breaking. It's got, again, multiple key lengths, does a lot more iterations. What's the problem with adding more iterations of the operation for the complexity? Instead of changing the key length or the block length, what's the problem with doing iterations to add the complexity?
It increases the work value.
Yeah. The work value for the attacker?
For the actual algorithm.
For the process, yeah. You have to take up more resources to do it. It slows everything down. Good. And it's Feistel type, using those blocks. What's Feistel doing? Splitting the message in half and using it to exclusive OR itself. Okay. Safer, used in Bluetooth. It's got either 64 or 128-bit blocks. And it's free. It's open source. Blowfish. Who created Blowfish? Bruce Schneier? Anyone read his books? Read his blog? Yeah. Good stuff. Very good stuff. It is very fast. Very fast. Again, algorithms may be very tough. The implementations may lend themselves to cracking. Two fish followed Bluefish. Schneier worked on the team that came up with the follow-up to Blowfish. And it's got multiple key lengths up to 256 on 128-bit blocks with 16 iterations, Gesundheit. RC5. Before we get to RC5, RC4. Do we still use RC4?
Yes.
Yes. Is RC4 a good algorithm?
Provided you don't give it weak IVs.
Yeah. What was the problem with using it as part of WEP? What was the implementation problem? The IVs repeated, didn't they? Way sooner than they were supposed to. They allowed some prediction, right? They were susceptible to a mathematical attack. Did that mean that the algorithm was bad? No. It was the implementation that wasn't so great. RC5, was that an improvement on RC4? Sure. It kept the key length up to 2040, increased the number of iterations, and it allowed larger inputs and variable inputs. Advantages and disadvantages. We talked about what Symmetric can do for you. They are fast, but the key management and distribution is difficult. we talked about how to transmit keys over an insecure channel. Or we talked about how to securely transfer keys. What's the best way to do it?
Out of band.
Out of band. Out of band. Don't use it over the same medium that you're sending encrypted traffic over. What's the other problem with Symmetric? They don't give you some of the capabilities that asymmetric algorithms do. Why? Why is non-repudiation not a part of it? Or authentication or access control?
You're not verifying who has the key?
Good. Good. You're relying on that key to not be compromised as the total sum of your security. And it only hits part of the triad, not all of it. Good. Questions before we go to asymmetric?